Welcome to the lecture 25 of the course Modeling and Ticket Simulation of Solar Photovoltaic Cell. In this lecture, we will cover some nanostructured solar cell structures, their working principle, and some numerical problems based on the topic we covered in this week. In last lecture, we have discussed organic solar cells, basic difference between organic solar cell and semiconductor material based solar cell also discussed. Perovskite solar cell, a typical structure we have discussed. Challenges of organic solar cell has also been described. In the present lecture, we will focus on nanostructured solar cell, also the bifacial solar cell. These are all actually comes in the third generation. And then we will go to the numerical problems which are related to the concepts we have cleared in this week, that is week 5. Nano-structured solar cell, it basically a radial p-n junction solar cell. Instead of planar p-n junction solar cell, so far we have discussed all are planar. So this is a new concept of radial p-n junction solar cell. Here the p-n junction that is formed around the radius of a nanowire or similar structure rather than a planar fashion as in a traditional solar cell. This design offers advantages in terms of light trapping and carrier collection, particularly for materials with short minority carrier diffusion lengths. This let us explain. We have discussed in thin film solar cell, in organic solar cells, in amorphous silicon based solar cells. We have seen that diffusion length of carrier in such materials are very less. Diffusion length less means if we increase the thickness of absorber layer, it will be meaningless because we know carriers generated within the diffusion length can be separated by diffusion followed by drift process. So to get more and more carriers, we can increase the thickness, but in that case, if the diffusion length is very less, increasing thickness beyond diffusion length will be useless. So for such type of materials, an alternative junction that is called radial p-n junction is important. In this case, propagation of light and flow of carriers after photogeneration, they are in orthogonal direction. But in case of planar structure, we have seen the propagation of light and separation of carrier and carrier flow are in the same direction. So what is the advantage with this? Let us see the structure first. This is the structure. A P silicon core, this is basically a circular cylindrical fashion, cylindrical structure, cylindrical shape with a diameter say R1, which is nothing but P silicon. This is called core, and around this we deposit or we develop in such a way that a cell of N silicon is developed. So this blue color indicates the P silicon and orange color, light orange color is the N silicon cell. If you observe here, the junction, p-n junction is formed radially from here to here. but light is incident from the top. Suppose this is the incident of light. So direction of flow of light from top to bottom, this vertically. But carrier flow will occur in this direction. Is the carrier flow direction. So within P silicon, whatever the excess electrons which are generated, they are flowing in this direction, and holes they are coming in this direction. So direction of carrier flow and propagation of light, they are opposite direction. Not opposite, they are orthogonal direction. What is the advantage of this? If the diffusion length is very less, that means we can set the radius of the core and radius of the cell accordingly, so that carriers will be generated within the diffusion length, not outside the diffusion length. Mostly or almost 100% carriers will be generated within the diffusion length from the junction or the depletion boundary. But that is not affected by light propagation. In case of parallel or lateral PN junction, if you see, from the junction and from the depletion layer, suppose this is the diffusion length, Pn, this is Ln, this is Lp. Light is also propagating in the left to right. So to increase more and more absorption, in this case, you have to increase the thickness. But if you increase the thickness where Lp and Ln is less, no usefulness of increasing thickness beyond Lp and Ln. But in case of radial PN junction, it is not like that. You can increase the height of the rod, which will increase more and more light, and that will not affect the carrier separation because carriers are separated radially. So this is the basic concept behind the radial PN junction solar cell. Height of rod can be increased to enhance absorption, which does not hamper carrier collection. And not a single such rods, there is array of such rods on a plane will serve as a nano wire array solar cell. So array of such solar cells will be like that, and contact is taken. One contact you may take from bottom side, from this in layer. One contact you can take, other contact you can take from the here. Through some tissue layer. tissue layer means is transconducting layer. And in such case of array of such nano solar cell, another advantage we can get, that is scattering of light. As the nanowires are very closely spaced in an array, in a say two-dimensional array along x-axis and y-axis on a plane, you can have more light will be captured due to incident of light at the side wall and due to multiple reflection in the side wall of the nanorods. This is another advantage. So optical absorption can be enhanced, as well as due to orthogonal direction of carrier flow and light propagation. They are independent to each other. They don't have any relation. That means you can increase height of the rod, maintaining some mechanical stability to increase the light absorption, whereas diffusion length is low, that is not a factor because carriers are separated radially and the radius of the core and cell may be kept in the order of diffusion length. This is very good structure for materials having low diffusion length. Say amorphous silicon, diffusion length is very less. For this structure is suitable. The advantage, enhanced light trapping. Light trapping means due to presence of closely spaced nanowire tips, nanorod tips. So every tips, that's just like a alternate refractive index in a pattern of refractive index variation on the surface. If you look from the top, so ultimately the incident light will be trapped within the structure, and also there are multiple reflection in the side wall. So more total generation of light will be much enhanced. Improved carrier collection, that already I have discussed, due to the radial separation of the carriers. Another important structure is called bifacial solar cell. Generally, whatever the structure so far we have seen, the back contact, which is full area back contact. That means if some light is transmitted through the solar cell or solar panel, whatever you are placing on top or rooftop, some transmitted light when coming from the solar panels, they may be reflected back due to aluminum back contact. But suppose some lights are reflected from the rooftop due to incident of solar radiation at different angles. So some radiations which are not coming on solar panel, which are coming at a different angle directly on the rooftop, and after reflection they may go towards the backside of the solar panel. In that case, if you have an option of incident light from the backside of a solar cell also, that will be obviously enhance the performance. So this concept is called bifacial solar cell. Also sometimes you have to put the solar cells almost vertically in vertical plane and slightly deviated from the vertical plane. In that case, light is coming in the both faces. Light is incident in the both faces. But due to the monofacial structure, so far we have discussed, the light which are entering through the front surface will only be useful. But in case of bifacial solar cell, if we can have an arrangement that light may incident from front and back both surfaces, then obviously the more and more light will be entering into the device. This is the concept of bifacial solar cell. And this bifacial solar cell is also important. The structure, what is the heterojunction with thin intrinsic layer, heat structure, already we discussed in some previous classes. That will be useful for bifacial application also. Also the pearl structure, the passivated emitter rear locally diffused. If we remove the back contact from the full area to a finger like contact, it will behave like a bifacial pearl solar cell. So let us see the structures. You see, these are the structures. This is a pearl bifacial solar cell. In this case, the contact, back contact is not full area contact. The locally diffused region with the boron atoms, this followed by contact formation in those locations. Passivation and ARC coating layer is still there. So light may incident from top and bottom in this case. So this behaves like a bifacial solar cell. Just we have modified the pearl structure conventional by putting the localized contact in the back side also. Another structure, that is a heat structure, we discussed earlier, based on the crystalline N-type silicon wafer. In both the sides there are amorphous intrinsic layer. Amorphous intrinsic layer, they are basically buffer layer to reduce the interface mismatch, and then on P plus layer, that is also deposited based on amorphous silicon, because this is deposited based on chemical vapor deposition technique. And in bottom there is a N plus side, N plus layer. So this PIN structure, basically PNN or PIN, this is very low doped wafer. This structure also, if you make the bottom contact just a localized contact instead of very full area contact, it will behave as a bifacial solar cell. So you can make the contact here like this. In this case also, light can incident from top and also from the bottom. So people are working on bifacial solar cell. In the simulation part, if possible, we will do the simulation for some bifacial solar cells also. Now let us move to some problems, numerical problems based on the structures we have discussed in last few lectures in this week. Some practical structures mainly will be considered in the problem. In this problem, we have considered a single crystal wafer based silicon solar cell. We have taken P silicon wafer and aluminum BSF technology, that is the fast successful industrial technology. solar cell. You observe the thickness of the observer layer is 250 micron, whereas emitter thickness is only 1 micron. And doping concentration of wafer and emitter are respectively 10 to the power 16 per centimeter cube, and it is 2.25 into 10 to the power 18 per centimeter cube. That means it is an asymmetric p-n junction like this. So n plus p junction. This is n plus, this is a p junction. So obviously the depletion layer width within the n plus region will be less, and depletion layer width within p region will be wider. Light is incident from the emitter side. Carrier concentration, intrinsic carrier concentration is given. Carrier lifetime for electron and hole are also given. For electron it is 800 microsecond, and for hole it is 800, both the same, 800 microsecond both. Mobility of electron and holes are compared respectively 1200 centimeter square per volt second, and for hole it is 400 centimeter square per volt second. Check whether the quasi-neutral region of wafer is fully covered by electron diffusion length or not. In p side, you know, the diffusion length of electron is important because carrier generated within the diffusion length can be separated. So let us consider the ln, diffusion length is here, ln. In the first part, we have to check whether the electron diffusion length ln is covering the quasi-neutral region of p or not. So we have to calculate ln, we have to calculate the depletion layer width also. Total thickness of p layer is 250 micron given. Anyway, we will go to the problem solution, but before that the second part let us see. This is determine the short circuit current density, JSC in milliampere per centimeter square if the incident optical power is 50 milliwatt per centimeter square at wavelength of 550 nanometer with uniform illumination. Uniform illumination means the decay in intensity of light or power of light with position, that is Ix is equal to I0 e to the power minus alpha x, should not be considered. Here you can consider uniform intensity of light, though it is absurd, but for sake of simplicity of the problem you can assume. Reverse saturation current of the diode is given 0.2 picoampere. Area of the solar cell, effective area is 4 millimeter square. Also this is given that dielectric constant of silicon is 12. Dielectric constant means relative permittivity of silicon, epsilon Rs as per our notation. Front surface reflectivity 0.3. Absorption coefficient 10 to the power 4 meter inverse. Number 3, also calculate the VOC, open circuit voltage, if the reverse saturation current is 0.2 picoampere. This is the problem. So we have to first calculate the depletion layer width considering asymmetric junction formula. You can use the complete formula, but it is not required. Approximately the depletion layer width will be extended 90% within the p region because doping difference is very high. Let us solve. So first calculate the depletion layer width, and to calculate depletion layer width, built-in potential is required. So we have to first calculate the built-in potential. So built-in potential formula is VBI is equal to VT. This is nothing but VT ln Na Nd by Ni square. Considering 100% ionization, if nothing is mentioned, so you can assume 100% ionization. That means doping concentration is same like a donor concentration. If you put the value 10 to the power 16, 2.25 into 10 to the power 18, Na square is 1.5 into 10 to the power 10 square, that is 1.5 square into 10 to the power 20. Vt value is 0.02585 volt, 25.85 millivolt, so this is 0.02585 volt. So this will be coming in volt. It is coming 0.83 volt. Built-in potential once find out. Depletion layer with formula W is equal to twice epsilon 0 epsilon Rs V built-in I Bi, which is built-in potential, by Q 1 by Nd plus 1 by Na to the power half. So approximately you can neglect the value of Nd 1 by Nd because Nd much greater than Na. So 1 by Nd negligible compared to 1 by Na. By putting these values, epsilon 0 is given 8.854 10 to the power minus 12. Vbi, epsilon Rs, that is dielectric constant, is 12. Built-in potential we have found 0.83, and Q value put ultimately 1 by Na 10 to the power 16. Yeah, here 10 to the power 6 to convert it per meter cube because all the units are SI units here. But here it was not required in case of built-in potential because this is a ratio. So here you don't need to convert. Both are centimeter per centimeter cube, it will be cancelled out. But be careful here, you have to calculate. You have to convert. After calculation, it is coming 0.332 micron, very small. Out of 250 micron, only 0.332 micron is covered by the depletion layer within the P region. So rest is quasi-neutral region. Assuming the depletion layer is fully inside the P silicon wafer only, because it is much less doped than N plus emitters, the quasi-neutral with 250 micron minus 0.332 micron, that is 249.668 micron. This is the quasi-neutral part. Now we have to calculate the Ln, diffusion length. Diffusion length is formulated by dn tau n. Dn, how can you get dn? Dn is not given, but you know the Einstein's relationship. Dn is equal to Vt into mu n. This is nothing but Vt. Vt is again room temperature. You can consider this 0.02585 into mu n is 1200 centimeter square per volt second. This volt cancelled, centimeter square per second. So 31.02 centimeter square per second. You convert it to meter square per second by multiplying with 10 to the power minus 4 because centimeter is equal to 10 to the power minus 2 meter. So centimeter square will be 10 to the power minus 4 meter square per second. Once dn is found out, tau n is given 800 microsecond. If you calculate, ln becomes 1575 micron, 1575. So see the thing. That means much greater than the total width of the P silicon wafer. So this is the ln value we have calculated 1575 micron. So depletion boundary will be long away, that is outside the device. That means here all the carriers generated within the quasi-neutral part, all excess electrons from the end, these excess electron will move to the boundary of the depletion layer by diffusion process starting from here. So we have checked that ln is much greater than 1575. So this fully under diffusion length. Here you may note that it is controlled by mainly the carrier lifetime. Suppose you are asked to calculate what is the minimum value of tau n to just cover the quasi-neutral part by diffusion length. What should be the value of tau n? What should be the minimum value of tau n so that the diffusion length will be exactly equal to the quasi-neutral part of the P region? You know the quasi-neutral part is 249.668 micron that we have calculated in last calculation. This will be dn into tau n say minimum, tau n min. If you calculate this, it will becoming 20 microsecond. That is 20 microsecond minimum value of tau n is required for covering the full quasi-neutral part by diffusion length. This tau n is again controlled by the defect centers we have discussed in case of Shockley-Riddle recombination. Anyway, so minimum 20 microsecond is required. If tau n is less than that, some portion remains left uncovered by diffusion length, that is carrier generated outside that region, outside the diffusion length, that will not be collected. But if it is more than 20 microsecond, all carriers generated within the quasi-neutral part will be collected and will contribute to the current. Now incident optical power is given. The second part, you have to calculate the short circuit current density, and wavelength is given 550 nanometer. And the formula for short circuit current density, you know, JSC is equal to Q times into generation rate LP plus Ln plus W. LP part you can neglect because within N side N itself is very thin. So almost equal to Ln. W also is very less compared to the other values. So this comparatively this can be equal to Qg into Ln in this particular case. Anyway, but how can you calculate G? First you have to calculate the generation rate. G is equal to alpha into incident intensity 1 minus R. Here incident intensity and intensity at any position x are equal because uniform illumination, considering uniform illumination, so I is constant we have assumed. R is 0.3. If you put the value, this 10 to the power 4 meter inverse, that is 10 to the power centimeter inverse. Anyway, you need to know the h nu value because in the formula, if you put the intensity value in milliwatt per centimeter square, you have to put h nu in electron volt and you have to then q multiplied by electron volt because the formula we have discussed earlier. So h nu electron volt will be 1.24 by lambda micron. It is becoming 2.255 electron volt. Alpha is also given. So G will be alpha 1 minus R P incident by area into 1 by Q into h nu, where h nu is electron volt, in electron volt, and P incident by area is nothing but I. Milliwatt or watt per area. So G is equal to, first we have put the, in centimeter, if we calculate centimeter 10 to the power 2 per centimeter inverse, 50 area is given. What is the area? Area is given 4 millimeter square. Okay, 4 millimeter square. And 50 milliwatt per centimeter square is the incident optical power. So 50 10 to the power minus 3 watt per centimeter square. That's why we have calculated it in per centimeter square. So G here also we have not changed. We have covered the alpha value per centimeter. So per centimeter square per centimeter cube. 1 minus 0.3 by 1 by q into 2.25, that is h nu value in electron volt. Electron volt into joule watt per centimeter square. In this way, if you calculate 15.52 by q into 10 to the power minus 1 per centimeter cube, that is nothing but 1.552 by q per centimeter cube per second, per centimeter cube per second. Now q is not put here because the q will be cancelled out in case of JSC. For 100% generation efficiency, JSC is nothing but q times g into this value, q g ln. So if you put the q, and this q will be cancelled out. That's why I have not put the value of q earlier. Ln must be greater than the quasi-neutral part. LP similarly much greater than quasi-neutral part in n plus emitter. But in the formula of this LP ln, you cannot put the ln, but because feasible value of ln is the width of the device. So if device is not present up to ln, so what is the need of using this value to put the JSC? So actually you have to, this is the catch of the problem here, you have to put the value of the device thickness, maximum wafer thickness you can calculate. That's why you can write 250 micron plus 1 micron of the emitter, maximum 250, or you can put 250 also. So the JSC will be q times into the G value 15.52 into 10 to the power minus 1, 15.52, that is 1.552, 15.52 10 to the power minus 1 by q into 251 into 10 to the power minus 4 per centimeter square. That's why area is not multiplied, because this is in the formula, you see area is not mentioned as it is a JSC value. So 10 to the power minus 4 is coming from this milliwatt, and this 10 to the power minus 1. 10 to 251 micrometer, sorry, it is from 251 micrometer. 251 micron means 251 into 10 to the power minus 4 centimeter. 1 micron is equal to 10 to the power minus 6 meter, that is equal to 10 to the power minus 4 centimeter. The JSC value will be coming ampere per centimeter square. This is a mixture of unit, ampere in SI and the centimeter square. So 38.95 milliampere per centimeter square, or 39 is the very conventional unit or very useful unit, milliampere per centimeter square, to represent the value of JSC. Once JSC is obtained, you can calculate the VOC. VOC formula is a VT ln 1 plus ISC by I0. In problem 8, 9 also we have used this. 0.025 85 ln 1 plus ISC is nothing but JSC into area by I0. JSC value is milliampere, 39 milliampere. So this ampere, 10 to the minus 3 ampere, that is per centimeter square. But here you have to multiply with the 4 millimeter square, that is 4 into 10 to the minus 2 centimeter area, centimeter square, 10 to the minus 2 because millimeter area 4 millimeter square, so 4 into 10 to the minus 2 centimeter square by 0.2 into 10 to the minus 12 because I0 reverse saturation current is 0.2 picoampere. Yeah, 4 millimeter square is equal to 4 into 10 to the power minus 2 centimeter square. After putting this value, the VOC will coming 0.589, that is almost equal to 0.6 volt, near about 0.6 volt. So here you have seen one thing, that in real structure this is asymmetric PN junction. In single wafer based silicon solar cell, what we are using, that is a single crystal based asymmetric junction solar cell. And diffusion length, if is more than the quasi-neutral part of the device, in the formula for JSC, that is photocurrent or short circuit current, don't need to put the value of diffusion length. You have to put the thickness of the device, because ln is more than that. No use of using the value of ln in the formula. This is an important note from this problem. So finally, in this lecture we have discussed some nanostructured, particularly radial junction nanowire array solar cell, their working principle and their advantages as discussed. The structure is suitable for low diffusion length material particularly. Bifacial solar cell structure has also been discussed, and this bifacial solar cell has advantage of absorbing more light. After that, some numerical problems. One numerical problem we have discussed basically on the practical solar cell structure we have solved, and we have seen that diffusion length is much greater than the thickness of the device. In that case, in formula you have to put the thickness of the device. There is a feasible value. And diffusion length plays a crucial role which decides the thickness of the absorber layer. If it is low, device thickness also should be such that the quasi-neutral part is of the order of diffusion length. Otherwise, unnecessarily increasing thickness, we will not get any benefit. Rather, we will get less current due to extra defect centers in the region where carriers generated cannot be collected or cannot be separated. This reference book of Martin A. Green you can follow for problems and different technologies of solar cells. Thank you.